Derivatives are an incredible thing. They have roles in finance, engineering, physics, AI, basically anything you can think of, really. Along with the integral, derivatives serve as one of the two main pillars of calculus. But no worries, we only need to tackle one of these today, so let's just stick to derivatives, shall we? Now, simply put, a derivative can be thought of as the rate of change at a specific moment. At one moment, for example, you might be driving at 30 miles per hour, while the next you're driving slightly faster at 32 miles per hour. That might not exactly sound groundbreaking, but being able to measure the changes in a function, such as the speed of a car, well, serves as the foundation for pretty much everything in our world, far beyond some fancy mathematics. You can think of this instantaneous rate of change like the direction you're facing when moving in a circle. As you walk, the direction is constantly yet gradually changing along with your movement. Now, before we try thinking about the rate of change at a specific point, the derivative, let's start by thinking about the average rate of change for a function. So if we go ahead and draw a line up here between these 2 points, what we have is the average rate of change for the interval of 0 to 2. And this is known as a secant line, and we can go ahead and call back to our good friend linear algebra to think about this rate of change. So what we have here is basically just rise over run, also known as change in y over the change in x. And if we go ahead and think about this, what we have here is a change of y of 4, because we have 4 minus 0, so we have 4, and then over 2. So that just gives us an average rate of change of 2. So 2 would be the slope of our line here. So we can just go ahead and write this as 2x. So that means that the average rate of change of our function for this interval is going to be 2. So our secant line, as we can see, for every 1x will increase by 2. So this gives us the average rate of change, but the derivative is the rate of change at a specific moment. So we're going to need to get a little more specific, because we can see that the rate of change is not evenly dispersed. For example, we have a much slower rate of change. It's increasing at a much slower pace along these lower values, while it's going up much faster up here, which is contributing more to this average rate of change. So what we can observe is that these outlier values, so these ones have a higher rate of change, for instance, and these values down here, which have a lower rate of change than our secant line, are going to play a major role in impacting the accuracy of our secant line. Because we can clearly see that while there are many values that the secant line seems to fairly accurately correspond to, it's also very disconnected from our actual curve here, which means it's only going to be of limited accuracy. And what this limited accuracy means, that if we want to find the derivative of a specific point, the specific rate of change, we're going to need to use another method, because this clearly isn't going to be accurate enough. If we want to find the rate of change, for example, for a value down here, or perhaps a value up here, we're going to need a secant line that isn't quite so inaccurate. Alright, so instead of wallowing in our misery, let's go ahead and try drawing another secant line. So instead of drawing a secant line on the interval from 0 to 2, let's try from 0 to 1. So if we try 0 to 1, we go ahead and get a line that looks a lot more interesting than our previous one, because we can see that while our first line was very disconnected from our curve, didn't really line up with it properly, our line down here actually is much closer, and that's because there is a smaller range of values that we're dealing with here. There aren't quite so great of extremes on either end. So what this means is that our secant line down here is actually more accurate than our previous one. And so if we take this to its natural conclusion, then if we try another secant line or yet another secant line, what we observe is that as we get closer to 0, the behavior of the secant line aligns closer and closer to the behavior of the curve. So what we're noticing is that as delta x, the change in x, decreases, the secant line is becoming more accurate. So if the accuracy of our secant line increases as the change in x, that is the distance between the 2 points, decreases, then how does that help us? Well, remember, the secant line is just a measure of the average rate of change, the rise over run, between 2 points. Now, if we're dealing with an infinitely small value as the change in x decreases, so as the change of x approaches 0, then what we're measuring here is basically the average rate of change over an infinitely small interval. So that's going to give us pretty much an exact snapshot of the rate of change for this very small interval. And what that yields is a very special line known as the tangent line. So we have the slope of our secant line as the change in x becomes infinitely small, and it gives us the instantaneous rate of change for a specific point. And this rate of change is what a derivative is. So the slope of this tangent line is the derivative of a specific point. So if we go up here, for example, and we go ahead and just approximate what our tangent line would look like, well, that is the derivative of this point. If we go over here, we can do the same thing. So we have a tangent line at around x is equal to 1, and this increase that we can measure, this tangent line, that is the derivative of this point. Alright, well, that's all great, but now we need to figure out how to find our derivative mathematically. We've been thinking about this visually, we've been thinking about this intuitively, but we need to actually be able to measure how much we're either ascending or descending at a particular point on our graph here. So let's go ahead and return to the formula for our secant line. And remember, this is just the average rate of change over an interval. So we can rewrite this as being y2 minus y1 over x2 minus x1, the change in y over the change in x. So now let's think about this in terms of the change in x, which is basically what gives us the length of the interval on which we're applying this average rate of change. So first, let's just go ahead and consider what y2 would be. So y2, we have 0 plus our change in x. So for this instance, it would be 2, since we have 0 plus 2. But let's go ahead and generalize it. So we'll take the function of 0 plus the change in x. And then we'll throw this into our function here, which is f of x is equal to x squared. But for now, let's just think about y1. So now we have y1. Well, if we're starting at 0, then y1 would just be f of 0. Okay, that's pretty simple. And then now we take the x values. So we have x2. Well, x2 would just be 0 plus the change x. And then for x1, well, x1 is just going to be, well, 0. So that means that we just have 0 here. And so now that we go ahead and simplify this, we can just cancel out these zeros. And now we need to figure out what this is equal to. So when we go ahead and take 0 plus the change in x and throw it into our function here, well, this is just going to get us the change in x squared. And then when we take f of 0 and throw it in here, well, 0 squared is just going to be 0. So this all cancels out. So what we're left with here is the change in x squared over change in x. And then we can go ahead and factor out a change in x, and that just leaves us with the change in x. So that means that the slope of our secant line is just going to be equal to the change in x. But if we go ahead and take a moment to remember here that the accuracy of our secant line increases as the change in x decreases, what we can do is we can take the limit of the change in x as x approaches 0, as the change in x becomes infinitely small. And that is going to get us 0, which means that the tangent line at x is equal to 0 is just 0. So what we've done is we've actually taken the derivative of a point here. So we can definitively say that the derivative of this point of f of 0 is equal to 0. Beautiful. So we have our tangent line here. So the instantaneous rate of change at x is equal to 0 is 0. Alright, so we've taken the derivative of a specific point on our function here at x is equal to 0. But now we need to employ some fancier math, because we're going to take the derivative of our function here as a whole. And what that'll do is yield us the derivative of every point on this function for a specific x value. So that would be the derivative of x squared, which is our function. So let's just get right into it. So in order to make this a little easier, I will go ahead and abbreviate the change in x as being equal to h. And this is very standard notation. In fact, you'll probably see this in most textbooks. And the main reason for that is because it's easier to write and it's easier to deal with. It's a little easier to manipulate. So anyway, let's just get right back to it. So we have y2. So y2 we can think about as being x for just some arbitrary point on our function here, plus h. And then we have minus y1. So y1, that means we would be starting from our point at f of x. And remember, this is very similar to what we just did previously, where we were going from 2 to 0 with a change in x. So anyway, now down here we have x2. So x2 would be x plus h minus x. Remember, we're dealing with some arbitrary x value and then the change in x. So now what we can do is very similar to previously. These two are just going to cancel out, and we're left with h down here on the denominator. So we have h, and now we need to throw these in to our function, x squared. So that means that we're going to get x plus h squared minus x squared, all of which is over h. And then we can go ahead and factor this out as being x squared plus 2xh, God, this is a doozy, plus h squared minus x squared. And of course, we can't forget this h down here. Now, thankfully, we can go ahead and cancel out two of these terms to simplify. So we have an x squared over here, and we have a negative x squared here. So these two cancel out, and we're left with 2xh plus h squared. And then now what we can do is we can factor out an h. So that gives us 2x plus h. So write that down here. So we have, as our final result, 2x plus h. But remember, if our change in x is going to be approaching 0 as we become more accurate, then that means that this h approaching 0 is just going to be canceled out, which means our derivative, so the derivative of our function here, is just going to be equal to 2x. So finally, after all that work, after this Sisyphean task of calculation, we finally get our derivative. So we have the derivative of our function of f of x is equal to 2x. Brilliant. Now, what's so incredibly helpful about finding the derivative of a function is that now we can use this derivative to find the derivative of all points on this function. So, for example, at x is equal to 0, we can go ahead and just throw this in. So we have 2 times 0, which is just 0. And we know this is accurate because we already found the derivative at x is equal to 0. So trying for another point now, at negative 1, for instance, if we go down here, we go ahead and construct a tangent line, well, we can just throw in our value here. So we throw in negative 1, and so 2 times negative 1 gets us a slope of negative 2. And then similarly, we can figure out that over here is just going to be plus 2. So we have a slope of 2 here, a slope of negative 2 here, and what about up here at x is equal to 2? Well, here, once again, we can just throw it into our derivative here. So we have 2 times 2, which gives us 4, which means that the slope here is going to be plus 4. And voila, there we go. So we've uncovered the mysteries of the derivative, we've solved for it, and now we can rest. Oh Christ, you gotta be kidding me. Well, thanks for watching. Have a wonderful day.